Guys, a few weeks ago, I purchased a large bag of Skittles. Here it is. And in the bag, there were 80 green Skittles. I actually kept them. 90 orange Skittles. I'm doing this just to entertain you. 87 purple Skittles. That's personally my favorite color. 69 red Skittles, which year after year, these are the Skittles that's the color that students prefer. I'm not sure why, but it's just what I see year after year. 88 yellow Skittles from a total sample size of 414. So we assume this bag represents one random sample of Skittles. So at the factory where they make Skittles, they just dump them into a giant vat, and then they mix them up, and then they just portion them into bags by weight. So I want to look at the proportion of red Skittles and the proportion of purple Skittles. So the sample proportion of red Skittles was 69 out of 414. So what percentage is that? 69 divided by 414, that's 16.7%. So that's the color students like. Here's the color that I like, the purple Skittles. So there were 87 purple Skittles out of 414. So 87 divided by 414, that's a little over 21%. So here's the thing. I have sample data on the percentage of these different color Skittles from my random sample. So let's explain why it's not appropriate to construct and interpret a confidence interval for the true difference between the proportion of red and purple Skittles produced using the two-proportion z-interval procedure, what we've learned in this lesson, in this context. So I'm interested in, can I find evidence that the company is making a different number of red Skittles versus purple Skittles? So I would like to capture the real difference between the population percentage of red Skittles produced and the population percentage of purple Skittles produced. I can see the sample difference is, around 5-ish%. So I can see that sample difference is around actually negative 5-ish% if you take red, the proportion of red minus the proportion of purple. But the point being, this is not an appropriate thing to do the way that these data have been gathered. So the question is, which of these conditions has failed? So the conditions for randomness, we need 2 independent random samples. This is an observational study. So not only do I need 2 independent random samples, so independent of one another, but then we would have to check the 10% rule because it's an observational study. So, and then in addition to that, then normality, the number of successes and failures from both samples should be greater than or equal to 10. So I'm going to give you 10 seconds. I want you to think about which of these conditions has failed. One of these conditions does not apply, and it means we cannot use this data in order to construct a two-proportion z-interval. 10 seconds. The condition that has failed is probably the most important condition. It's the randomness condition. So yes, we're acting as if this bag is one random sample of Skittles. But here's the problem. In order to do or construct a two-proportion z-interval, or even to calculate a two-proportion z-test, to execute that test, I need 2 independent random samples. I don't have 2 independent random samples here. I have only 1 random sample, and I am classifying observations in that sample as being either red or purple in this case. But let's explain why they're not independent of one another. So there are only 414 Skittles in this bag. So let's say that there were 5 more red Skittles. So let's actually say that the proportion of red Skittles was actually 74 out of 414. Well, wait a second. If there's more red Skittles, what that means is that we have to have fewer of the other Skittle colors. So maybe that means we have 1 fewer green Skittles. We have 1 fewer red, 1 fewer yellow. Maybe there's 2 fewer purples. So if this goes up by 5, the truth is this proportion is not independent of this sample. This value could go down by 2, 3, 4, by 5. So if one of these proportions changes, that implies that the other proportion might change also. They're not independent of one another because they both come from the same sample of 414 Skittles. So the bottom line, you can't use the data the way this has been collected in order to calculate a 2-proportion Z interval because we do not have 2 independent random samples. There's only 1 random sample of Skittles. So here, I'll even tell a story. So consider if the proportion of red increases in the sample, that forces the proportion of purple, that proportion of purple could decrease. They're not necessarily independent of one another. So the proportion of red Skittles in the sample, the proportion of red Skittles and purple Skittles in the sample may depend on one another. In other words, for instance, more red may mean fewer purple Skittles. So just because it looks like the data are set up for a particular procedure, it's important to always check your conditions. It's important to consider randomness, independence, and normality whenever you're building a confidence interval or doing a significance test, performing some type of inference procedure.